All right, today's lecture is going to focus on how concentration affects the rate of a chemical equation. And from that, we get something that's called a rate law. A rate law is a mathematical equation that can be utilized to calculate the rate at which a chemical reaction will occur at if we know the concentrations of all the reactants and something called their orders. Now, the rate of a reaction is only dependent upon the reactants, because it's the reactants that are colliding with each other to form the products. Now, how to write a rate law is very important. As you can see, to write a rate law, this is what the mathematical equation will always be. You must always write the word rate, and that rate of that chemical equation is equal to K. Now, K is called the rate constant, okay? And it's a variable that changes with temperature. And this is why when the temperature goes up, that usually means that the rate constant increases because it is dependent upon temperature. And that will then cause the rate of the reaction to be faster because the K, the rate constant, increases with temperature. All right? We multiply that rate constant by the concentration of the reactants in this equation. That would be A and B. And they are then raised to a variable which is called a power or an order. That order is looking at how many molecules of each of those substances are involved in the collision, the chemical reaction. Now, the orders, which is M and N in this equation, you'll notice I purposely did not make sure to use little a and little b because the orders do not necessarily need to match the coefficients. They can match them, and that is called an elementary process, and these are things we'll talk about in another lecture, but they don't have to. And we won't figure out those orders until we look at experimental evidence, which is primarily what this lecture is going to be focusing on. Now, what are the orders? What can they be? The orders can be anywhere from 0, 1, or 2. These are the most common three orders you'll see on the national exam. I have never not seen them be one of those three values. So I expect the orders to be one of those three. If M equals 0, that is called a 0th order reactant. If it's 1, it's first, and if it's 2, it's second. Okay? A 0th order reactant means that there are none of those molecules are involved in the collision that affects the chemical reaction. Therefore, we would get a rate law that would look like this. Rate equals K times the concentration of A to the 0th power. Any number raised to 0 is always going to give you 1. So therefore, whatever the concentration of A is, it doesn't make a bit of difference, whatever the value is. As long as we do have some of it present, we must have some of it or the reaction will not occur. But it doesn't matter if I change its concentration. It will not affect the rate of the reaction. So any substance that's 0th order, okay, its concentration, okay, does not affect the rate law or the rate of the chemical equation. If it's first or second order, then it does. So if it's first order, we see this rate law. Rate equals K times the concentration of A raised to the first power. Now, if I were to double the concentration of the substance, if I were to replace this and double it and make it 2A, okay, 2 to the first becomes 2A times K, I would end up getting a value that is 2K or twice as big. So when I double the concentration, the rate of the reaction is increased by a factor of 2, or it's twice as fast. If I triple it, 3 raised to 1 is 3. The rate would also triple, so the rate of the reaction would be 3 times as fast. Okay, so if the reaction occurs in 100 seconds, it would only occur in 50 seconds if I double it. The rate would be twice as fast, so it would take half as much time for it to completely react. Okay? If it's second order, now we have to square it. So if I have this rate law, rate equals K times A to the second power. If I were to double A, 2 squared means 4. It would quadruple. The rate would be 4 times faster if I double the concentration of the reactant. If I triple it, we get 9. It'd be 9 times faster. So based on what happens. If I change the concentration of a reactant and the rate of the reaction does not change, then I know that that reactant is 0th order. It therefore would not be included in the rate law because its concentration doesn't affect the chemical reaction rate. If it's 1st order, it's pretty simple. If I double it and the rate doubles, or it's twice as fast, then I know the reaction is 1st order. So that's how we can experimentally derive the orders of the reactants, is by simply changing the concentration of it while I hold all the other variables the same. I would keep the temperature the same. I'd keep the size of the reaction vessel the same. I'd keep everything else the same. The only thing I would do is I would double the concentration of it, and I would see how it is affected. If I double the concentration and the rate does not change, then it's 0th order. If I double it and it doubles, then it's 1st order. If I double it and the rate is 4 times faster, then it's 2nd order. And that's how we can experimentally derive the orders of the reactants. Once I know the orders, I can then write my rate law. All right, so let's go ahead and do a few examples of this. Now, before I get there, I forgot to mention one thing. That is the overall order of a reaction. The overall order of the reaction is simply the summation of all the orders of all reactants. So let's say my rate law is rate equals K, concentration of A to the 1st, concentration of B to the 2nd. 1 plus 2 would be 3. So the overall order of this reaction would be 3rd order, or 3. Okay, and what that really means, we'll talk about this in another lecture, that means that 3 molecules need to strike each other in order for the chemical reaction to occur. And we'll get into talking about how orders leads into number of molecules, and that'll be into another lecture. But for the most part, the overall order is just simply the summation of all the orders of all the reactants in the rate law. All right, so now let's look at how you might be posed a problem on the national exam and how you can figure out the orders of the reactant. Here we have a chemical reaction in which we have only one reactant, and therefore I can write the rate of the reaction as rate equals K, the rate constant little k, times the concentration of the reactant, and it is raised to a specific order. And I can make it any variable, any letter I want, X, A, M, all right? But I don't know the order of the reactant, and I don't know its concentration. So this is what I can immediately write from any chemical reaction. I can write it. The only thing I don't know would be the order on it. So what I do now is I do experimental evidence. So here I see an experiment where I did trial 1, in which I had a specific concentration of the reactant, 0.1 molar, and then I am able to calculate the rate of the reaction. I could graph it like we saw in the last lecture, and from the graph we could figure out the rate of the reaction from the chemical experiment. Then, after I've done it maybe a couple times and I get an overall average rate, I then will change the concentration of it and I'll see if the reaction changes. So here we can see that by doubling the concentration, the rate of the reaction has changed. So changing its concentration does immediately tell me that X cannot be 0 in this situation. Okay, it cannot be 0 because the rate of the reaction is changing as I change the concentration. And therefore, I know that it has to have an order on something other than 0. Now, how do we do this? One way is by doing it mathematically. And what we simply do is we write the rate law in one of the trials, and I divide it by the rate law of another trial. Okay, so the rate law is, again, rate equals little k, concentration of reactant to the x, divided by the rate of another trial, little k, concentration over x. So typically what I like to do is always pick having the larger rate over the smaller rate. So what I'm going to do is I'm going to look at trials 2 and 1. So the rate of reaction 2 divided by the rate of reaction 1. This is how we experimentally show proof of figuring out the orders of the reactants. All right, so now I plug in chug what I have of the rate law. So the rate of the reaction is 0.34 molar per second equals K times the concentration of the reactant is 0.2 molar to the X value. I'm going to divide that then by the first trial, which has 0.085 molar per second equals K times 0.1 molar to the X. Now, by dividing this, a couple things happen. First of all, you'll notice that we have K divided by K. The rate constant, K, does not change if the temperature is held constant. So as long as the temperature is constant, the K1 and K2, or any of the Ks, the rate constant, any of these trials, will be equal to each other because the temperature is not changing. So again, as being a good scientist, you'd keep all of the variables constant and just look at how changing the concentration of that reactant affects the rate. So the Ks will cancel when we do this. Now if I divide 0.034 by 0.085, I end up getting 4 equals. Now this is where you learned in algebra properties of logarithms. If we have a number raised to a specific logarithm or exponential, we have a mathematical expression where I can then move those two variables into each other as long as they're raised to the same exponent power. This is all values that you've learned in your Algebra 2 class. So now if I drive this down further, 0.2 divided by 0.1 gives me 2 to the X. So dividing the rates of the reaction, I get 4 equals, the concentrations you'll notice is twice as big, 2 to the X. Therefore, what does 2 need to be raised to that will cause you to give me a 4? X needs to be 2. If X is 2, this tells me that this is a second order reactant. And therefore now I've proven my order to be second order. So rate equals K times CH3CHO raised to the second order. This right here is the rate law for this chemical reaction. Okay? This is called the rate law for the rate expression. And this is how we calculate it. If they say calculate or determine the rate law of the chemical reaction, this is what you'd want to show. Okay? All right, let's do another problem. Now let's look at a problem where we have two reactants. So here we have a chemical reaction. And now because there's two reactants, what we'll notice is that between the different experimental trials, we will change the concentration of one of the substances, but the other one must be held constant. We must do this so that we can just see what each one is by changing just one of the substances, how it affects the rate of the reaction. And then we'll keep the other one constant, like in trials 4 and 5. We'll keep them constant, and we'll now change the other variable and see how the reaction rate changes. Okay? All right, so let's go ahead and look at each of these. So this is the type of mathematical work you'll need to do a problem like this. All right, so the rate law would be equal to little k times the concentration raised to the x times the second substance raised to the y, all over a second trial. So again, we will make sure when we write these rate laws, the rate laws again are only going to come from the reactants, because it's how quickly those substances collide and react is what dictates the rate of a chemical reaction. The products do nothing when it comes to the rate of a chemical reaction, because it's the reactants that are forming the products. All right, so if I've already identified trials 1 and 2 as two trials I want to pick because I've kept the other substance constant. So let's plug and chug everything that we know. So the rate of this chemical equation, okay, again, I'm going to go with the greater rate, which was trial 2, because it has a greater concentration. I'm going to put that on top. So the rate of the reaction is 0.010 molar per second equals K times the concentration of 1 molar to the first. All right, divided by the concentration of hydroxide ion, which is 0.05 molar, to the y, all divided by 0.005 molar per second K times 0.5 molar to the x, 0.050 molar to the y. All right, so now what cancels out of here? Okay, again, we'll always assume that the temperature is being held constant, so the rate constant will cancel. And because hydroxide is kept constant, this whole entire term also cancels out because it's exactly the same expression. Doesn't matter what y is, it's the same in both cases. That's why we must keep all of the other reactants constant, so we're only looking at one reactant concentration effect at a time. Dividing here, I get a value of 2 equals 2 to the x. So what must x be that 2 to what power gives me 2? Which would be very easy to identify. X equals 1. And therefore, CH3, 3CBr is first order as a chemical reactant. Because by doubling its concentration, the rate of the reaction has doubled. Okay, and therefore it's first order. Now we've got to do the same thing for Y. So now we are going to look at finding the order of the hydroxide ion. And sometimes in the national exam it might be good to say I'm going to go ahead and look at trials 5 to 4 to find Y, the order with respect to Y. All right, looking at those trials over here, 0.010 molar per second equals K times 1.0 molar. Now I do know the order with respect to X, which is 1, because we just figured out as first order. So I can now plug in that extra additional information that I know. 0.2 molar to the Y, all divided by 0.010 molar to the X, molar per second, excuse me, equals K times 1.0 molar to the first and 0.1 molar to the Y. All right, see what cancels out. The K's cancel. 1 molar to the first over 1 molar to the first. That cancels. Again, because we keep it the same, it cancels out of the expression. 0.01 divided by 0.01 is 1. 1 equals 2 to the Y. What must Y be for 2 to it to equal 1? And hopefully you know that it's 0. Any number raised to the 0th power gives you 1. Therefore, the hydroxide ion is 0th order. Okay, to write the rate law from that, we'll now go ahead and plug in the orders. So the rate of this chemical equation will be rate equals little k, concentration of CH3, 3Cr to the first. And because hydroxide is to the 0th, any number there raised to 0 is effectively going to be 1. So whenever we have a 0th order reactant, we don't even need to include it as part of the rate law. So right there, right there is the rate law, the experimentally derived rate law for this chemical reaction. Okay? So that's how we can mathematically determine the orders of the reactants of all the reactants. You could have more than even 2 reactants, finding them one at a time and showing mathematical support for how we can figure out the orders of the reactants. Okay? All right. There's a second way that we can figure out the orders of reactants without having to do the math. That is through explanation. For example, we can say this. To find the order of CH3, 3CBr in trials 2, the concentration of it was doubled compared to trial 1, and the rate of the reaction doubled. this indicates, oops, ran out of room there. This indicates that CH3 CBr is a first order reactant. You could also get the credit for determining the orders of the reactants by simply writing it out as you see it. I double the concentration of CH3CBr, I keep the hydroxide concentration the same, and the rate doubled between trials 2 and 1. Therefore, if I double the concentration of one of the reactants and the rate doubles, it must be first order. But in order to receive that through explanation, you have to be that type of detail. And if you're worried about not being able to provide that type of scope and detail, then it's recommended to go ahead and do the rate law of 2 of the trials comparisons and do it mathematically. So you can do it mathematically, or you can utilize explanations in order to get the validation, as long as you talk about the change in concentration while holding the other ones constant and how the rate is affected by it. If I do the same thing with trials 4 and 5, I would say in trials 5 and 4, I've kept the concentration of CH3CBr constant while I doubled the concentration of hydroxide ion. The rate of the reaction did not change, therefore changing the concentration of hydroxide did not affect the rate of the reaction, and therefore the order with respect to hydroxide ion must be 0th order. So that's another way of figuring out the orders of chemical reactions is through explanations and not by using mathematics. Again, you can pick whatever way you prefer to utilize. All right, let's go to the very last problem. So on page 3, here's a rate reaction, and I would like you to figure out the orders of the 2 reactants, which is A and B. We never have to worry about C because, again, it's the reactants that determines the rate of the reaction. So pause the lecture now and do like I just showed you in the previous problem and figure out the orders of A and B utilizing the mathematics presented to you. All right, hopefully you paused the lecture and went ahead and tried to do or figure out the orders of the reactions. And mathematically, this is where what I've shown up above in letter A. I looked at trials 1 and 2 because A was kept constant, but B was doubled. So again, writing the rate law, again, we always put the rate of the reaction, which is going to be given to you. And that always is the initial rate of the reaction, so it's the rate of the reaction immediately once the reaction begins. So rate equals K times the concentration of A raised to different powers. We'll notice that the K's cancel and A cancels out of it because it's the same, and we get 1 to the 2y. Therefore, y must be 0. B is a 0th order reactant. Now, you could have explained, looking at trials 1 and 2, we kept A's concentration the same, but we doubled B. Doubling B did not affect the rate of the reaction since it was the same in both trials 1 and 2. Since changing the concentration does not affect the rate of the reaction, it must be 0th order. That's another way we could figure out the order of B using explanation. Trials 3 and 1, we double the concentration of A while keeping B the same. Again, the K's cancel as long as the temperature is held constant. And we get now 4 equals 2 to the X. X is number 2. So A is a 2nd order reactant. The next thing they typically will ask you is to write the rate law based on the experimental evidence. And that's what I did for you down here. You would write down this for your rate law. Rate equals little k times the concentration of A squared. Again, B is not included in it because it's a 0th order reactant. And that is the rate law for this chemical equation given. Now, there's a couple other things that they might typically ask you to do in a problem like this. The next thing they could ask you to do is to figure out the value of the rate constant. How do you think we can figure out the value of the rate constant from the data? What could we do to figure out K? And hopefully right now you're saying to yourselves, oh, I just need a plug and chug. That is correct. We can pick any one of the 3 experiments, doesn't matter which one it is, because the temperature is being held constant, and we can plug in the values and we can see what the rate constant will be. So that's usually the next thing you need to do. All right, so let's go ahead and do that. Let's pick trial 1. So in trial 1, Okay, 4.0 times 10 to the negative fifth molar per second is the rate. I don't know K. The concentration of A in trial 1 was 0.10 molar squared. Okay, because second order. B we don't plug in because it's 0th order, doesn't affect the rate law. All right, solving for K, we'll divide by 0.1 molar squared. Divide by 0.1 molar squared. All right, so going ahead and do the math. 4 times the negative fifth divided by 0.1 squared. And the value of the rate constant ends up being 4.0 times 10 to the negative third. Your calculator should give you a value of 4.0 times 10 to the negative third. Now the hard part on here is this is typically very important. On the national exam, the units of K are typically worth 1 point on the FRQ. That's a very important point to gain. Students really struggle on figuring out the units of the rate constant. How do we figure that? Well, if we look at the units, and again, most students don't plug in the units, we're going to get molar per second divided by molar squared, since it was second order. Molar times molar is molar squared. Can you now simplify this down with looking at just letters without numbers that you can easily plug into a calculator? So molar per seconds would be how I would write it, times the reciprocal is how we're able to do this. So now we have a molar on top and 2 molars on the bottom. So one of them will factor out. Or you could have also multiplied across and had molar over seconds molar squared. Reducing down, we end up getting 1 over molar times seconds. That is the units on the rate law, 1 over molar seconds. Okay, so you have to take the rate units, which is typically molar per second, divided by the number of molars, which is equal to the overall order of the chemical equation. Okay, and then you simply always will take the molar per second times the number of molar orders it is based on what the overall order of the reaction is to figure out the units of the chemical equation. Now, if I were to pick a different trial, should I get the same K value? Does it matter which trial I pick? Well, theoretically, it shouldn't. So go ahead and do trial 3 right now and calculate the value of the K, pause my lecture, and see if you get the same value. All right, so going ahead and doing the math, I end up getting exactly the same answer. Hopefully you did as well. So again, it doesn't matter what trial you pick. So once you figure out the rate law, you can then substitute in one of the trials of the experiments, doesn't matter which one, plugging in all the variables that you know of that chemical reaction and solving for K. And again, figuring out the units of the rate constant is actually a very important concept. It's one of the few places on the national exam that units might be worth points in the overall problems. Lastly, the last thing they could do is they could ask you to figure out what would the initial rate of the reaction be if I now change the concentrations of A and B to something totally different. Since I now know the rate constant and I know the orders, I can now substitute into the rate law to figure out the rate of this chemical equation no matter what concentration I want to run this reaction at. So again, this becomes another simple plug and chug. So go ahead and see if you can do C by plugging into the rate law, now knowing that we know both K and the order, and figuring out in letter C there what the initial rate of the reaction would be based on these given concentrations. All right, by plugging in, again, the concentration of B is not really needed to be known because it's 0th order, so we're going to plug in the value of K, the concentration of A squared, and we end up getting 1 times 10 to the negative 3, or 0.001. Again, the units should end up being molar per second. Let's see what happens. 1 over molar times seconds times molar squared. Again, now one of the molars will cancel, and now I'm left with molars, a molar on top and a seconds on the bottom, and I have units of molar per second. So again, the units of the rate constant end up working out, giving us the units which are molar per second. So now I have a homework where I've got like two or three different problems utilizing all these different facets of, first of all, figuring out the orders of each of the reactants, writing the rate law, and then using the rate law to figure out the rate constant and maybe the rate of the reaction at different various concentrations. These are all aspects. It's, again, nice thing about this is it's a process, much like stoichiometry, it's a process. But you just got to do enough practice that you get really good at the process. And once you are, you can do this, you'll be able to easily memorize this even after a couple months and still be able to do problems like this. The key right now is do enough practice so you get really good at this stuff and can do this on the test at the end of this unit in a couple weeks. All right, thanks again for listening.